Hello there. In this video, we are going to discuss detailed solutions of all the questions those were appeared in GATE 2013 with respect to analog circuit. These are the question numbers which are appeared in GATE 2013 pertaining to analog circuit. We will discuss solutions of each and every question one by one. First question is question number 10. In this question, a circuit is given with an op-amp and a transistor configuration. Now what is asked is we have to find out what is the output voltage, and it is also given that the op-amp is ideal. So before solving this kind of problem, what are the procedure we should follow? First we should check by considering the op-amp as a comparator. Then we see if there is any negative feedback or not. If there is any negative feedback, then the virtual ground concept then will apply. So these are the three points we should check while solving op-amp problem. Now the first step is, if we take the op-amp as a comparator, then 5 voltage is present at the inverting terminal and 0 voltage, that is grounded, at the non-inverting terminal. So if we draw the circuit will be, the V minus will be 5 volt and V plus will be at 0 volt. So if you see, the V plus is less than V minus, or V minus is greater than V plus. So as V minus is greater than V plus, so the output voltage will saturate at minus V sat, that is minus 15 voltage will be there at the output voltage. If the minus 15 voltage will appear across here, then what will happen? This PN junction or this NPN transistor, this base emitter junction will get forward bias, because only 0.7 voltage is required here and we have 15 voltage available for biasing this junction. So as this junction will get forward bias, so what will happen? Next, the second step is to check if there is any negative feedback or not. As V output voltage is minus 15 volt, then V of the Q is at minus 15 volt and VB is 0, but this is only 0.7 voltage is required to forward bias this junction, but available voltage is 15 volt. So that means this junction will get forward bias, and once this junction is get forward bias, then IC or IE collector current will flow across this, hence there will be a negative feedback. So we can apply the virtual ground concept. Okay, so junction will be forward bias, VV junction will be forward bias, and VV will be maintained at, and once this junction is forward bias, it will be maintained at 0.7 volt. So the V potential will be at minus 0.7 volt. So transistor Q will be on, that means negative feedback will exist. Once the Q will be on, there will be negative feedback because of the current will flow, and there will be negative feedback. Because of the negative feedback, we can apply the virtual ground concept, that is here the potential will be same as this potential, that is it will become zero potential at both inverting and non-inverting terminal. So the output voltage is nothing but the same as the V voltage, that is minus 0.7 volt. So the output voltage will be minus 0.7 volt, hence B is the correct answer. Thank you. Next question is question number 15. If you see, in this question a feedback circuit is given. We have to find out what is the characteristics of input impedance and output impedance with respect to this feedback configuration. If you see, at the input, the voltage, input voltage and the feedback voltage is in series configuration, and whereas at the output, the voltage is taken parallelly from the output, or the sampling is done parallelly with the output voltage. That means this is a shunt configuration. So the input is series configuration and the output is shunt configuration. We can always remember the series configuration means the impedance will increase, and the shunt configuration means the impedance will decrease. So if you see at the input, as it is in series configuration, the input impedance is increasing and the output impedance is decreasing. So if you see among the option, the input impedance is increasing, the output impedance is decreasing, A is the correct answer. So among the option A is the correct answer. Thank you. Next question is question number 30. In this question, it is given that the knee current of the Zener diode is 10 milliampere, that is the minimum current that is required for the Zener action is 10 milliampere, and the Zener voltage is given, that is 5 volt. Okay, we have to find out. We have to find out what is the minimum value of RL and the minimum power rating of the Zener diode. What is the power rating and what is the minimum value of RL? That's what we have to find out. So what is given? That is the knee current of the Zener diode is given 10 milliampere and the Zener voltage is given to be 5 volt. First let us find out what is RL minimum. So we can name this current as I, this current as IZ, and this is the load current. So you can apply KCL at this point. So if you apply KCL at this point, 10 minus 5 volt, because this is 5 volt, so 10 minus 5 divided by 100 ohm equal to IZ current plus IL current. IZ plus IL. IL is nothing but VZ by RL. VZ by RL. Again, VZ is 5 volt. So if we simplify this, we will get an expression RL in terms of IZ. So RL is dependent upon IZ. Now we have to find out what is the minimum value of RL. For RL to be minimum, this denominator value should be maximum. For this denominator value to be maximum, IZ should be minimum. So for RL to be minimum, IZ also to be minimum. But IZ cannot go below 10 milliampere, because below 10 milliampere there won't be any Zener action. So IZ minimum value is IZK, that is 10 milliampere. Okay. So if we solve this, we can find out what is the RL minimum value. That will be coming out as 125 ohm. Okay. So RL minimum value we are able to find out. Next, we have to find out what is the power rating of the Zener diode. Power rating is nothing but that is the maximum power that can be handled by the Zener diode. So that is in the worst condition, it can allow that much of maximum current to flow across this Zener diode. So if due to some disturbance or something will happen, this load will be disconnected, then the maximum current can be flowing through this Zener diode. So in that case, this Zener diode will be able to sustain that much of current. So here is the KCL, that is 10 minus 5 divided by 100 equal to IZ plus IL. Now due to some disturbance or something, if IL is disconnected, that is IL load current is becoming 0, then through the Zener diode the maximum current will flow, that is the supply current, that is 50 milliampere will flow. So that maximum current will give us the power rating of this Zener diode. So power rating is nothing but the product of the voltage and the current, maximum current that is flowing across this Zener diode, that is VZ into IZ max. VZ is 5 and this is 50 milliampere. So if we put, and we can get, so 250 milliwatt is the minimum power rating that is required for this Zener diode to sustain any kind of disturbance across the circuit. So 250 milliwatt is the power rating and 125 ohm is the minimum resistance of RL. Hence B is the correct answer. Thank you. Next question is question number 34. In this question, an NMOS transistor is given. We have to find out dVV by dID value of this transistor, and this Kn value also given. Threshold value of the voltage is also given to be 1 volt, and it is given that there is a negligible body effect, okay, or the channel length modulation. So if you see in the question, as here the gate and drain of this transistor is shorted, so this transistor will be always in saturation region. So as the gate and drain are shorted, the transistor will be always in saturation region. Hence we can write the saturation current equation as Kn by 2 VGS minus Vt whole square. Okay, so Kn value is given. VGS is nothing but Vg minus S. Vg is nothing but Vb minus Vs. Vs equal to 0. So if we simplify this, we can get Id in terms of Vb. Okay, so Id equal to Kn by 2 Vb minus 1 whole square. If we differentiate this Id with respect to this Vb, we can get the transconductance Gm of this transistor, that is Gm equal to del Id by del Vb equal to Kn. Okay, but in the question we have to find out what is the small signal resistance. The small signal resistance is nothing but inverse of the transconductance gain, that is 1 by Gm. If we put the value, we can get what is the small signal resistance. That will be coming out as 25 kilo ohm. So B is the correct answer. Thank you. Next question is question number 35. In this question, an NMOS transistor is given in which the transconductance of the transistor is given to be 1 milliampere per volt, and we have to find out what is the lower cutoff frequency with respect to this capacitor. Okay, the lower cutoff frequency will be given by this capacitor and these two resistors. If we draw the circuit, that is, if we draw this portion of the circuit, then it will be looking like this. So the frequency of this circuit will be 1 by 2 pi R equivalent C. R equivalent will be looking at this point. If we look at this point, this RD and RL will be in series. So the frequency will be 1 by 2 pi R equivalent is nothing but the summation of both the RD and the load resistance RL. So every value is given. By putting, we can get the cutoff frequency to be nearly 8 Hz. So, and that's what in the question it is asked, the approximate value of the lower cutoff frequency, and that is 8 Hz. Hence the correct answer is A. Thank you. Next question is question number 41. In this question, simply two op-amp amplifier circuits are cascaded here. We have to find out what is the output voltage. Suppose voltage at this node is V1 and at this node is V2. So if we see there is negative feedback, hence the virtual ground concept will come into play. So V1 voltage will become 1 volt. So because of the virtual ground concept, V1 voltage will become 1 volt. Now if I1 current is flowing through this branch and I2 current is flowing through this branch, then we can apply KCL at this node, that is I1 equal to I2, that is minus 2 minus V1. V1 is nothing but 1 volt divided by 1 kilo ohm equal to 1 minus V2 divided by 1 kilo ohm. So by solving this, we can get the V2 voltage as 4 volt. Now if we see, this circuit is nothing but a non-inverting amplifier. If we name this resistor as R2 and this as R1, then we can find out what is the output voltage. That is, output voltage is equal to 1 plus R2 by R1 whole into V2. V2 is 4 volt, R2 and R1 value is given, so the output voltage we can easily get as 8 volt. Hence, among the option C is the correct answer. Thank you. Next question is question number 43. In this question, there are basically 4 diodes, okay, and voltage is applied across this YZ terminal, and we have to find out what is the voltage across this WX terminal. So sinusoidal voltage is basically applied across YZ terminal. We will analyze the circuit for both positive half cycle, negative half cycle, and we will see what is the output voltage across WX. So VYZ is applied as 1000 sin omega t. Let us analyze the circuit during positive half cycle. During positive half cycle, if you see, this is positive, means this will be open circuited, this will be open circuited because they will be reverse biased. Similarly, these two will also be reverse biased. Hence, if we redraw the circuit during the positive half cycle, the circuit will be looking like this. So as there is no current flowing through this or through this, so the voltage VWX will be 0 during the positive half cycle. Wx will be 0 during the positive half cycle. Now during the negative half cycle, this will be forward bias, this will be forward bias, similarly this will be forward bias, all the 4 diode will be forward bias. So the circuit will be looking like this. So if you see, this potential at this Z point is same as W. Similarly, potential at Z point is same as X. So both are at same potential. That means again the voltage across BWX is 0. So BWX is 0 at both positive and negative half cycle. That is, BWX is 0 at all the time. Hence the output voltage is 0 at all the time. Among the option D is the correct answer. Thank you. Next question is question number 46. In this question, a transistor circuit is given and it is given that beta value of the circuit is very high. We have to find out what is the value of R2 that will produce a collector current of 1 milliampere. Okay. So as beta has very large value, then we can assume this base current to be very close to 0 and this collector current will be nearly equal to emitter current, that will be 1 milliampere. Okay. So suppose the potential at this point is VB and the potential at this point is VE. So we can easily find out what is VE because we know the current and this resistance is given. So VE is nothing but IC into RE. IC is 1 milliampere and RE is equal to 0.5 K. Okay. So the VE voltage will be 0.5 volt. Hence VB we can find out because this 0.7 volt will be added to VE, that will give us VB voltage. Okay. So VB voltage is nothing but 0.7 plus VE, that is 1.2 volt. Okay. VB voltage is 1.2 volt. This potential, now we know this potential. Okay. We have to find out this R2. If we apply voltage division at this point with respect to this VCC, then VB is nothing but 3 into RC divided by R2 plus 60, because VCC is nothing but 3 volt. Okay. So here if we write 3 R2 divided by R2 plus 60 is same as this VB voltage, that is 1.2 volt. So we have only one variable, we can easily solve and find out what is R2. That will be coming out as 40 kilo ohm. Hence among the option C is the correct answer. This concludes analysis of all the questions those were appeared in GATE 2013 with respect to analog circuit. If any question is missing or any questions are missing, please let me know so that those can be added in this part. If you have any query or suggestion, please let me know. I will be happy to address those issues. See you in the next lecture. Until then, stay safe, stay healthy, and most importantly, keep preparing harder and harder. Thank you.